You're standing on the 80th floor of a skyscraper. The city stretches out below you in every direction. And then you feel it. A slow, almost imperceptible shift. The floor beneath your feet moves. The windows flex. A glass of water on the table beside you tilts slightly and the surface ripples. Most people who feel this for the first time grip the nearest solid object and look for the exit. But here is the truth that changes everything. The building is not failing. It is working exactly as designed. In fact, if it weren't moving, you would be in far more danger than you are right now. Today we're going inside the engineering that keeps the tallest buildings on Earth standing. And the answer is not what most people expect. It is not about making buildings stronger. It is about making them flexible enough to survive. And by the end, you'll understand why the skyscraper that sways is the one keeping you alive. Let's start with the wind, because most people have no real sense of what wind actually does to a tall building. At street level, wind is something you feel on your face. It pushes against you, maybe knocks your umbrella inside out. But at 300 meters above the ground, wind is a completely different force. It doesn't blow in a steady stream. It arrives in pulses, in gusts, in complex, swirling patterns created by the building's own shape cutting through the airflow. At that height, wind speeds can reach well over 150 kilometers per hour, and the pressure those speeds generate against a flat glass surface is enormous. A single square meter of glass facade on a skyscraper at that height can experience a force equivalent to several hundred kilograms pushing against it every second in shifting directions. Now multiply that across thousands of square meters of glass and steel. The total lateral force trying to push a super tall skyscraper sideways on a windy day is measured not in tons, but in thousands of tons. What makes this force particularly dangerous is not its raw size, but its behavior. Wind at high altitude doesn't push uniformly from one direction. As it flows around a tall building, it creates vortices on the downwind side, spiraling columns of rotating air that peel off alternately from each side of the structure in a pattern called vortex shedding. These vortices don't push the building in the direction the wind is blowing. They push it sideways, perpendicular to the wind, in a rhythmic alternating pattern. Left, then right, then left again, at a frequency determined by the wind speed and the building's width. If that frequency happens to be close to the building's own natural frequency of vibration, the results can escalate very quickly from uncomfortable to dangerous. This is the phenomenon that keeps structural engineers awake at night, because unlike a simple steady push, vortex shedding is self-reinforcing. The more the building moves, the more organized the vortex pattern becomes, and the more energy it pumps into the structure. Before a single steel beam is ordered for a super tall building, engineers spend months studying the wind. Every major skyscraper project today goes through an extensive wind tunnel testing program. Engineers build a highly detailed scale model of the proposed building, typically somewhere between 1 to 400 scale, and place it inside a boundary layer wind tunnel, a facility specifically designed to simulate the turbulent, irregular wind conditions that exist close to the ground in a dense urban environment. Around the model, they also build scaled replicas of the surrounding city blocks, because the presence of nearby buildings fundamentally changes the way wind flows around any structure. Pressure taps covering the model's surface record wind forces at hundreds of points simultaneously across dozens of different wind directions. This testing process can take 6 months and cost millions of dollars before a single foundation pile is driven into the ground. And sometimes it sends engineers back to the drawing board entirely, because the wind tunnel reveals that a beautiful architectural form is aerodynamically disastrous. For most of human history, buildings solved the wind problem the same way: mass and rigidity. Make the walls thick enough, the foundations deep enough, and the structure heavy enough, and the wind simply cannot move it. This works perfectly well for buildings up to a certain height. But somewhere around 150 to 200 meters, something changes. The building becomes tall enough and slender enough that a new physics problem emerges, one that mass and rigidity alone cannot solve. The problem is called resonance. Have you ever pushed a child on a swing and noticed that if you time your pushes exactly right, each small push adds to the last, and the swing goes higher and higher? Wind does exactly the same thing to a tall building. At a certain wind speed, the natural frequency of the gusts begins to match the natural frequency at which the building wants to vibrate. Each gust adds a little more energy to the building's movement. The oscillations build. And in a structure that is too rigid to absorb and redirect that energy, the results can be catastrophic. The most famous demonstration of resonance destroying a structure is the Tacoma Narrows Bridge in 1940, which tore itself apart in a 64 km/h wind, not because the wind was unusually strong, but because its frequency matched the bridge's natural resonance exactly. But the Tacoma Narrows wasn't the only lesson engineers learned the hard way. In the 1970s, the John Hancock Tower in Boston, a sleek 60-story glass skyscraper, began experiencing such severe wind-induced oscillations after its completion that occupants on the upper floors reported motion sickness during storms. The building swayed so dramatically that objects slid across desks, and some workers refused to come in on windy days. Engineers eventually installed a pair of 300-ton tune mass dampers to bring the movement under control, but the episode became a landmark case study in what happens when resonance is underestimated during design. A building that looks perfectly solid from the street can, under the right wind conditions, become almost unusable for the people inside it. Engineers building skyscrapers in the mid-20th century understood the resonance lesson and faced a fundamental design problem. You cannot make a super tall building rigid enough to resist resonance, because the forces involved are simply too large. But you also cannot let the building oscillate freely, because the accelerations felt by the people inside would be nauseating and eventually structurally damaging. The solution, when it finally arrived, was one of the most elegant ideas in the history of structural engineering. Instead of fighting the movement, use the movement itself to cancel itself out. This is the principle behind a tune mass damper. The concept is deceptively simple. Inside the building, usually near the top where the oscillation is greatest, engineers install a massive weight, typically a steel or concrete block weighing hundreds or even thousands of tons. This weight is suspended on cables or bearings and connected to the building structure through a system of hydraulic shock absorbers and springs. The system is precisely tuned so that when the building begins to sway in one direction, the damper weight swings in the opposite direction. The two movements partially cancel each other out. The building still moves, but the amplitude of that movement is dramatically reduced. On paper, this sounds almost absurdly simple. In practice, getting the tuning exactly right is an extraordinarily complex engineering challenge, because the damper must respond correctly across a range of wind speeds, frequencies, and directions, in a structure that is itself changing its resonant frequency slightly as temperature, occupancy, and loading conditions shift throughout the day. The most famous tune mass damper in the world sits near the top of Taipei 101 in Taiwan, once the tallest building on Earth. It is a steel sphere nearly 6 meters in diameter, weighing 660 metric tons, suspended by 8 steel cables from the 92nd to the 88th floor. The sphere is painted gold and visitors can see it from observation platforms. It moves visibly during typhoons and strong wind events, swinging up to 1.5 meters in either direction as it works to counteract the building's sway. Engineers at Taipei 101 report that the damper reduces the building's peak acceleration by around 40% during major wind events. Without it, the upper floors would experience lateral accelerations that would make standing upright difficult and cause significant discomfort to anyone inside. But Taipei 101 is far from the only example. One World Trade Center in New York uses a system of fluid viscous dampers built into its structural frame. The Shanghai Tower uses a combination of its spiraling exterior form, which is specifically designed to reduce wind load by up to 24% compared to a flat-sided building of the same height, and internal damping systems. The Burj Khalifa in Dubai uses its distinctive Y-shaped floor plan and setback structure to break up wind vortices before they can build into dangerous resonant frequencies. The Petronas Towers in Kuala Lumpur use outrigger trusses that connect the inner concrete core to the outer steel columns, creating a structure that distributes lateral wind loads across the entire building cross-section rather than concentrating them at any single point. Every super tall building built in the last 50 years carries within it some version of this same idea, that the most dangerous thing a tall building can do in strong wind is refuse to move. There is also a human dimension to all of this that the engineering textbooks rarely discuss. The people who live and work inside these buildings experience the sway directly. In the upper floors of super tall towers during strong wind events, occupants report a sensation best described as a slow, rhythmic rolling, similar in some ways to being on a ship at sea. Objects on flat surfaces shift. Suspended lights sway. In some buildings, the movement is accompanied by a low structural groan as the building's frame flexes under load. One engineer who worked for years on the upper floors of a Chicago tower described the experience this way. On the worst days, you don't see the movement. You feel it in your inner ear, the same faint signal your body uses to detect whether you are standing still or not. It takes weeks before your brain stops flagging it as a reason to be afraid. Most people adapt. But that first week, almost everyone holds the desk. Workers in the upper floors of towers like the Willis Tower in Chicago describe learning to read the building's movement the way sailors read a deck, adjusting their balance automatically after weeks of working at height. But the psychological challenge for new occupants is real, and building engineers now work closely with psychologists to ensure that the accelerations experienced in occupied floors stay well below the threshold that causes discomfort, even if the structural movement itself is significant. The internationally accepted comfort standard for office buildings limits the peak lateral acceleration that occupants should feel to no more than 10 to 15 milligrams of gravitational force during a 10-year storm event. That is roughly the sensation of tilting your head slightly to one side. The building may be moving half a meter at its tip, but what you feel in your chair is almost nothing. Getting from half a meter of movement at the top to almost nothing felt in the occupied floors below is the entire challenge of modern skyscraper engineering, solved invisibly, every day, in buildings that most people walk past without a second thought. The next frontier in this field is moving beyond passive damper systems toward active and semi-active control. A passive tune mass damper responds to whatever the building gives it. An active damper uses computer-controlled actuators to apply precisely calculated counterforces in real time, reacting to sensor data from across the building structure. These systems can respond faster and more precisely than passive weights, and they can adapt to changing wind conditions as they develop rather than being tuned to a fixed frequency. Some newer systems use magnetorheological fluid, a liquid whose viscosity can be changed almost instantly by applying a magnetic field, allowing engineers to change the damper's behavior in milliseconds. The Burj Khalifa alone has over 350 sensors embedded throughout its structure, monitoring wind pressure, structural strain, and acceleration in real time, feeding data to systems that can respond to developing wind events before occupants feel anything at all. What started as a swinging steel ball has evolved into something closer to a building-scale nervous system, constantly sensing, calculating, and responding to keep a structure that weighs hundreds of thousands of tons balanced against forces that never stop trying to push it over. And here is what that means the next time you feel a tall building move beneath your feet. The sway you feel is not a warning. It is the answer. It is the product of decades of engineering refinement, built around a single insight that took engineers most of the 20th century to fully accept, that in a world where the wind never stops, the structure that survives is not the one that refuses to bend. It is the one that knows exactly how much to give. If you want more deep dives into the hidden engineering keeping the world standing, subscribe. What's coming next will be even more interesting.